Okay, yeah. Hello, everybody. My name is Mark. I want to talk about how we can study atmospheric gravity waves in a laboratory using a gas centrifuge. This is joint work with Marie Rodal from Free University Berlin. For a motivation, I want to give a quick reminder about gravity wave life cycle. So a typical gravity wave might be excited at a mountain range, and then it propagates upwards, also horizontally, away from the source, and thereby gets bigger and bigger in amplitude. And this is due to the thinning air, to the thinning background air, in combination with energy conservation, such that the amplitude grows. We have seen it in talks of Robert, for example, where you get these really big amplitudes if you go to the right altitudes. And so then such a mountain wave can only maintain such a large amplitude as long as it doesn't break. At a certain point, it will break due to nonlinear processes, and it will overturn and dissipate. And a lot of the phenomena that I've just described have been studied also in experiments, but all of these experiments have in common that they were done with stratified water as the working fluid, but phenomena like the altitudinal growth is really due to the compressibility of air. So wouldn't it be nice to have an experiment where we really have compressible waves? And also, recent studies show that the nonlinear dynamics that I mentioned that are important for the breaking of the wave are influenced also by the compressibility, which is not present in water, like, for example, modulational instability, self-acceleration, or secondary wave generation. So here's the idea. I want to convince you that we should use gas centrifuges as an experimental device to study our gravity waves. The basic idea is to substitute the gravitational force by the centrifugal force. So the gravitational force is actually rather weak. So the stratification that we would get in a laboratory would be very, very weak if we just rely on the gravitational acceleration. We would need a huge vessel to excite a gravity wave in there. But what if we substitute with the centrifugal force in a gas centrifuge? So the idea is to have a cylinder filled with gas, then you spin up the centrifuge, bring the bulk to solid body rotation, and then you would also have a stratified gas in the centrifuge, and this would excite waves, or you can excite waves in these circumstances. The question, of course, is, do these waves compare? Are these waves in a centrifuge similar to waves in the atmosphere? And I want to convince you that this is actually true. So this is based on a theoretical study. We did mathematical analysis in this setup here. We have a cylinder of radius r0 with spins with an angular velocity of omega. And we are on radial coordinates. So we have a azimuthal angle phi and a radial coordinate r, and the height is z. And here on the right, just to show you that we are considering the full compressible Euler equations in all dimensions. Yeah, but then we do some assumptions without loss of generality. We assume that the waves or the perturbations that we put in these in the solid body rotation are actually symmetric. And we assume that the wavelength that we want to excite is small in comparison with the total radius of the centrifuge, which gives us a scale separation parameter epsilon, which we assume in the following to be 0. Also, we consider, or we focus on a shallow layer close to the rim. So we assume that our coordinate r divided by r0 is of order 1 as epsilon goes to 0. And now we do the typical asymptotic analysis, perturbation theory. And what we find is the following. We can compute then the dispersion and polarization relations of the perturbations in the centrifuge. And we find indeed that the dispersion relations looks, at least to leading order, completely the same as in the atmosphere, which is a nice surprise. So what I plot here is on the x-axis q, which is just a non-dimensional measure for the angular frequency. On the y-axis is kappa, which is the azimuthal wave number. So you can think in the atmosphere of the horizontal wave number. And yeah, we have two cases here for the horizontal wave number, an isotropic and an anisotropic case. In the isotropic case, it is assumed that the azimuthal wave number is of the same order as the radial wave number, whereas in the anisotropic case, it is assumed that the azimuthal wavelength is much longer than the radial wavelength. And what we find here are three regimes in the angular frequency, a high, intermediate, and low regime. And I want to point out the intermediate regime for the isotropic case. Here we find the gravity wave dispersion relation and also the acoustic wave dispersion relation, but they are scale separated. So we could measure in this regime nicely our gravity waves. They look exactly the same, and the acoustic waves, which have much larger frequency, our measurements wouldn't be spoiled by that. If we go to the low angular frequency regime, we also find acoustic waves and then Boussinesque gravity waves. This is what the BGW stands for. So here we would find the same dispersion relation, though these gravity waves have no altitudinal amplification. So here the altitudinal amplification would be the radial amplification. So you wouldn't see this, this amplification that the amplitudes would get larger if you go to the center of the centrifuge. And then there's also the high angular frequency regime where you find acoustic gravity waves. So you find the complete dispersion relation and no scale separation. So you cannot probably distinguish between the acoustic and gravity waves then. And if you go to the anisotropic regime, you find the same thing, but like in the atmosphere with if you put hydrostatic in front of it, so like the hydrostatic gravity waves or the hydrostatic acoustic waves. And yeah, also showing here the higher order asymptotic. So we go to next order, not only the leading order as we do a series in terms of epsilon. And here I show for the particular case of the intermediate regime, because we find this the most interesting one, also the next two leading order terms. So you can see here the frequency is exactly the same to leading order as in the atmosphere. For yeah, you have the Brunt-Väseler frequency, which is equally computed. But and this is of order of the Brunt-Väseler frequency, but to the next order you get a correction, which is of order epsilon. And to remind you, this is the wavelength, the typical wavelength in comparison to the radius. So as long as this is small, also this term here would be small. But to show what it does is here we have a dispersion diagram. So the wave number, so this is the horizontal or azimuthal wave number, and the frequency. And the gray circles are the leading order. And then here the blue circles with the crosses are the correction to the next order. So this is plotted for a rather high epsilon, already like 0.2, I cannot remember exactly. So it does something, but as long as epsilon is small, this is not so big. And here is a plot to give you an idea about the ballpark if you want to design such a centrifuge, about the design specifics. So here I plot the frequency measured in RPM, so how fast it has to spin over the radius. And I plotted here in this diagram some typical commercially available centrifuges, like, for example, a typical laundry machine, which has maybe a radius of 20 centimeters and then spins maybe with 1000 RPM or a little more. But then there's also the clinical centrifuges, this gray dot, which is used in hospitals to analyze blood, for example. And then here at the top of the plot, we have the ultracentrifuge and the modern Zippet type gas centrifuge. Those are huge centrifuges that are used in uranium enrichment, so for nuclear power plants or other things. And the blue lines here represent now the points that we should choose if we want to design a centrifuge that is in the intermediate regime, so that has this nice properties of yeah, that we can have gravity waves in there. And yeah, for air, if we use air as a working fluid, it's a little bit larger. Whereas if we fill it with xenon has better properties. We can even go lower with the frequency, so we don't have to spin it as much. This is due to the heat capacity at constant pressure of xenon, which is much smaller than this of air. All right. So next question would be, how would we excite gravity waves in the centrifuge? And I could present two methods. Either so both starts with having a modulated outer rim. So you put here a topography of whatever you want. You could like model a real mountain if you like, and then you spin the centrifuge up to a certain angular frequency such that the entire bulk is in solid body rotation, and then you spin it up a little more. And due to inertia, the solid body rotation remains, whereas now the rim has a differential velocity, and this would excite a wave. Another possibility would to have an inner cylinder and an outer cylinder spinning with different velocities, which would induce a shear velocity in the wind in the centrifuge. And this would be kind of the same setup that Francois Lott presented in his result. This would also excite a gravity wave over such a mountain range. How would we measure that? One could use in situ sensing, so either wall shear stress sensors or pressure sensors, though it is questionable if these sensors would survive a centrifuge, because in this intermediate regime, this would be like if we would build a centrifuge of like 50 centimeters radius. In the intermediate regime, it would need to spin with 10,000 RPM. And yeah, this is already thousands of G-forces for a sensor. And then there's also the question, how do you get the signal of the sensor out of the centrifuge? So it's probably smarter to do remote sensing. So either temperature with infrared cameras, or, which is my favorite, to do it with a laser. So you couple a laser into the centrifuge, then have a mirror in the centrifuge, and then go back out. So you have also the analysis outside of the centrifuge. And from the intensity variations, you could infer the density. And from the density, you could infer the entire wave field by the polarization relations that we just derived here. And with this, I want to draw your attention to the paper where we put all of this together. So if you like to read it, yeah, you're welcome. And with this, thank you for your attention.
Yeah, thank you very much for this nice talk. Do we have any questions?
Hi, thanks. Very nice talk. I have a experimentalist question. Do you know the characteristic wavelength of the excited waves, and do you know if you can actually measure that?
Yes, so this is the beauty about it. You can excite whatever waves you want. So it really depends on the topography that you modulate your outer rim with. So you can have large waves, small waves, you can excite monochromatic waves. So you can really decide what characteristic wavelength you want. The problem, of course, is here in the analysis, your wavelengths, your characteristic wavelengths needs to be smaller than the radius of the centrifuge. So this really gives you a bound of how big you need to build a centrifuge. So I envisioned like a centrifuge of having a radius of like 50 centimeters, and then to get a nice epsilon of like 0.1 maybe, to make these errors that I presented in the higher order asymptotics not being too big. Then you can have characteristic wavelengths of 5 centimeters. And I think this should be completely realistic to measure with like a laser, for example.
Okay, yeah, thank you.
Do we have any other questions? Yeah, Rival.
Yeah, very nice talk, Mark. I have two small questions. One, you derived the dispersion relationship close to the rim, and to take advantage of the compressibility, you want waves to propagate towards the center. And do you have any idea of a forcing that could be varying the boundary? I'm thinking of the Plummer-McEwen experiment. Do you imagine you could get a QBO in your thing?
So to be honest, I only got, please keep the microphone because I only got the first question, but yeah, I first answered that. So I boldly claim without loss of generality, we concentrate at the outer rim, but actually you can generalize it quite nicely to go really into the bulk. And what you find is, so you can completely drop this assumption of being in a shallow in a shallow layer close to the rim. And for that, we use WKB analysis. And what you find is the same wave field that you would get in the atmosphere, but it is warped. So everything is warped towards the center of the centrifuge. So the actual wavelength gets smaller and smaller and smaller towards the center, but everything else stays the same. And what was the second question?
I'll tell you about the second question offline later, but that convergence towards the center, how will that affect any wave mean flow interaction that you might look into?
Yeah, that would be essentially exact. So everything is warped. So it would be the same as in the atmosphere. So it is, what is it called mathematically? Isomorphic. So this is what we prove also in the paper.
Okay, so then there we have another question over there by Lucas.
So I'm sorry, not an experimentalist, so perhaps a naive question, but in this rapidly rotating centrifuge, wouldn't you get Coriolis effects that are very strong compared to the real atmosphere? Or yeah, how would that deal? How would you deal with that?
Yeah, this is a very good question. So as you can see in our equations here, we consider the Coriolis force. It is here, and in contrast to the atmosphere, the Coriolis force is in the same plane as our centrifugal force. So whereas on the atmosphere, so they are perpendicular, here they are in the same plane. So it does something. And this is exactly the reason why we don't get the exact same dispersion relation, but get these higher order corrections here. So this is why in the higher order correction, we have an omega here. This is due to the Coriolis force. So this is what happens. So the Coriolis force has an impact. And what it does is here, you can see in the dispersion diagram that it tilts the dispersion branches a little bit. But yeah, it's not too bad. As long as your wavelength is small enough, the effect is negligible.
Thanks a lot.
Okay, yeah, thanks again for this nice talk. And then we move on to the last one.